The first step in getting our laser to work is to remove contaminants from inside the tube. If we were, for example, to put in helium and neon gas and turn it on, it would never operate the first time because there's traces of air gases adhering to elements of the tube itself, such as the cathode and the anode and other parts of the tube. So in order to remove these contaminants, we inject helium into the tube at a pressure of a few torr and energize the tube. During this procedure, helium atoms are fairly energetic and they bounce off the tube walls, scouring off or removing air gases and things like that that are adhering to the tube walls. After a few minutes of this, and this process is called electron bombardment, we'll simply open up the manifold to the high vacuum system and flush out all the helium along with contaminants that have been dislodged from the tube walls. This procedure will be repeated several times in order to continually lower the amount of contaminants in the tube. After 3 or 4 of these flushes, we can then put our neon and helium gas mix inside the tube, and hopefully the contaminants are low enough that the tube will actually operate properly. Before we completely evacuate the helium flush that we put inside the laser tube, it's instructive to use a mass spectrometer to check the level of contaminants that are inside that mixture. Looking at what's left inside of this, we find a great deal of helium as expected, but we also find water vapor and even traces of air gases such as nitrogen and oxygen. These contaminants are at a fairly high level if we can see them at all on this graph, in which case the laser itself would definitely not operate with this level of contaminants. We'll now evacuate that flush and then put in a fresh helium gas to do it all over again. Of course, before we do this, we'll stop the RGA, turn off the filament, and then open the valve. With the RGA filament turned off, it's now safe to open up the evacuate valve, which connects the laser tube and the manifold directly to the high vacuum pump to evacuate it. We'll evacuate the entire system until the manifold gauge reads 0, and then give it about another 5 minutes or so to bring it to as low a vacuum as possible. At that point, we'll put fresh helium back in the system after we close the evacuate valve, run the tube for another few minutes to once again allow electron bombardment to remove remaining contaminants, and do it all over again. Every time we do this, we'll lower the percentage of the contaminants inside the tube relative to the amount of helium. Having run about 3 flushes now, the tube should have had a reduction in contaminants to a level which will allow the laser to operate. So it's time to put in the correct neon and helium gas mix. I close off the evacuate valve to isolate the tube and the manifold from the rest of the system. I then inject neon gas to approximately 1 torr. I've injected a little bit too much, so I'll use the evacuate valve to bring this down to 1.04 torr neon. I will now backfill with helium. I'm looking for a ratio of 7.5 to 1, so I'm going to fill this to a total pressure of 8.5 torr. Now the tube itself appears to have that neon color, but it's certainly not lasing right now. The total pressure is far too high. So I reduce that pressure using this evacuate valve until hopefully a beam appears for the laser itself at about 3.7 torr. At this point I have approximately the correct gas mix and I have approximately the correct pressure. here's the output of that laser again as it appears on a white piece of paper in front of it. The output is by no means optimal. However, it does appear. The pressure right now is likely far too high. The next step is to use a power meter to measure the output from this laser and then reduce the power in increments of say 0.1 to 0.2 torr until you figure out the actual optimal pressure for this tube. The power meter is showing us approximately 1/4 of a milliwatt right now at a pressure of 3.5 torr. If I begin reducing the tube pressure gradually, you'll see the power increase. 0.26, 0.27, 0.28. 0.3, 0.4 milliwatts, 0.45 milliwatts at about 2.7 torr total tube pressure. At this point, it appears that reducing the total tube pressure actually results in a weaker output. So there is an optimal tube pressure. And by graphing the total pressure of the tube versus the optical power output of this laser, we can determine what that what the proper pressure is for this particular tube. Of course, now that the laser is operating properly, we can determine not only the optimal pressure for the tube, but also the exact ratio of gases that we actually have inside the tube using our mass spectrometer. Furthermore, we can also determine the percentage of impurities inside the tube right now. We realize that when the impurities exceed a certain level, the output power of the laser suffers and eventually the laser stops operating. Using the mass spectrometer, we can ratio gases that we want to gases we don't want to determine the actual quantity of impurities inside the gas mix that's operating right now. You can see the effects of pressure on the output of a helium-neon laser a little more dramatically by looking at the white piece of paper as I reduce the pressure. The mix is about the same and the total pressure is about 4.7 torr, which is where lasing starts. I'm going to reduce the pressure now gradually and you'll see the effects. As we approach 4 torr, you see the output increase. Three and a half torr. Around 3 torr, and we begin to see optimal output. Two and a half torr, output starts to drop. Two torr, still operating. 1.5 torr. You can see the output begin to drop off till somewhere around 1.1 torr, where it simply stops oscillating.